Okay, so let's talk about special relativity. Let's see if we can try to make sense of some of the things that we saw in yesterday's video. For example, I don't know if we'll get to all of it today, but we saw that the video talked about time being different, length being different for things approaching the speed of light, mass being different. Did the video talk about simultaneous events? I can't remember if the video talked about that. So we'll talk about some of the concepts that come out of special relativity, okay? So one of the things so special relativity is based on two ideas, right? The first idea is that if you're in a frame of reference that's not accelerating, that's what an inertial frame of reference is. It's a reference that's not accelerating. So in other words, if you're standing still, or you're traveling in a car that's moving at a constant speed, the laws of physics are the same. So for instance, if I'm standing still and I throw a ball up in the air, it will behave in a certain way. It will behave exactly the same way if I'm traveling in a car at a constant speed and I throw the ball up in the air in the car. It's going to do the exact same thing. It's going to go up, it's going to come down, and it'll be a parabola when it does that, right? So the behaviors are the same. That's the first set. And that's something that we talked about in grade 11. Okay? Something we talked about in grade 11. The second one we'll talk about a little bit today is that the speed of light does not change, which is weird. Because if I shoot, for example, a cannonball, right? If I shoot a cannonball at a target, let's say, for instance, I shoot a cannonball at a target, and a cannonball has a speed of 100 meters per second. Now, let's say the cannonball is on a moving target, and let's say the moving target has a speed of 20 meters per second. How fast would I perceive that cannonball approaching me? It would be 100 and what? 120, right? It would be just, and that's what you learned last year in grade 11. However, light would not be different. So imagine this, imagine that you're measuring the speed of light from the headlights of a car. It has a value, 300,000 meters per second. Now imagine the car is traveling towards you, and it turns its lights on, and you measured the speed of light, it would still be the same value. Now that's weird, and we talked about this yesterday, but we never really went into, because you're just accepting that as fact, right? Like you're just accepting that piece of information is true. But how do we know it's true? I'm telling you that it's true, but how do you know it's true? I could be lying to you, right? I could have made it all up. So what I'm going to do is I'm going to show you an experiment that kind of led to the idea that this is the case. Okay? The experiment is called the Michelson-Morley experiment. The experiment was actually set up to prove something. Now, in grade 11, you guys talked about waves, right? Okay. A wave is a disturbance in a what? Starts with an M. The medium, right? So what would be the medium for the disturbance that I am generating right now that you're picking up with your ears? Sound, but what's the medium? It's air, right? Now, here's the thing. There was a whole bunch of debate as to whether or not light was a wave or a particle. Okay, and we'll talk more about that later on in this course. Whether or not light was a wave or a particle. If light is a wave and waves need a medium, the question then was, what was the medium that light was traveling through? So they made up this thing called the ether wind. Okay, this medium, that invisible medium that you couldn't see, but you could detect. So this experiment was set up to show the effects of this medium on light. Let me show you the experiment, okay? So this is the experiment. By the way, this is in your course outline. Okay, this experiment. So the idea is you take I'm actually going to turn. So imagine that there is no medium. Okay, there's no medium, right? What's going to happen is I'm going to shoot a beam of light. The beam of light will split, and this is the equal distance. Okay, so you'll see it. Like, beam of light will split, return to another mirror, and then you could detect it. Okay? Now, what if there was a medium? How would that affect you? What do you think that would? How do you think that would affect your results? One of the beam of lights would have to travel against the medium, right? Which one would it be? It would be the one that bounces this way. It's going to go with the medium, but then it's going to go against the medium. Okay? Do you think that they will return to this point at the same time? What do you think? The prediction was that they wouldn't. Because to me, it would be like a swimmer. Imagine this is a swimmer that we duplicated the swimmer. One swimmer went this way and the other swimmer went this way. We know that if this was moving water, it would affect the motion of the swimmers, right? But here, this is what happened. When they did the experiment, they noticed that the speed of light did not change. It was exactly the same. There was no effect. Whether or not the predicted medium was traveling faster, or there was no medium, the results were always the same. So when they measured the speed of light, they saw that it always came back at the same point. And that was like, well, how could that be? What this did was it showed that there was no medium, but it went one step further. Einstein said, you know what? This is actually showing us that the speed of light doesn't change. It doesn't matter which way you're looking at it. The speed of light is constant. So it's not like a swimmer in the water where, in grade 11 you said, what's the speed? Imagine you're on the shore and there's a swimmer in the water and there's a current of the water and we said, what's the speed of the swimmer? This is not like, light is not like this at all. It does not get affected by the medium. Okay? So that's where the second point came from. The principle of invariant light speed. Okay? So the Michelson-Morley experiment showed that there was no medium, but it also led Einstein to the discovery that the speed of light doesn't change. Trivia question. Who was the name of the scientist that actually calculated the speed of light? It was in the video. Yeah, James Clerk Maxwell, right? He showed that the speed of light was, they use it in miles per second, but it was 183,000 miles per second. Okay. So, those are two big ideas, right? So let's talk about how those two ideas led to something like time dilation. Now, the idea of time dilation is that something that's moving will have a slower clock. Okay? So let's see if we can figure out what. So you saw that in the video yesterday, right? You saw that, things that are moving versus things that are stationary, the clocks don't tick at the same rate. Now let's figure out why. Okay? So let's imagine that we have a light clock. So this is a light clock. Now, a clock is something that it moves at a regular interval, right? So you can make a clock out of anything. As long as it moves at a regular interval, we can make a sundial, right? Which is a clock, and that's based on the motion of what? The Earth around the sun. We can make a clock using electricity, because there's a frequency there that we can tap into. Imagine we make a light clock, okay? So the clock will tick based on how long it takes the beam of light to go from this point to this point back to this point. Okay. But now, if you're stationary, sorry, all these little things come up here, or at least if you think you're stationary, it's going to just travel in a straight line. But remember in the video, if you're observing something that's moving, so in other words, if you take this light clock, but you apply a velocity to it, now it doesn't look the same to a stationary observer, right? It would be like this. Imagine I take a ball in the air, and I'm in a car, and I throw it in the air. If I'm in a car and I'm traveling, right, I throw it in the air, where's that ball going to land? It's exactly in the same place, assuming I throw it directly up in the air. It's going to go up, and it's going to come right back down where I threw it from, right? Assuming I don't throw it at an angle. I just throw it straight up, it's going to come right back down. But if I'm watching the person in a car doing this, it wouldn't look like that. It would look, how? It would look like a parabola. Why? Because the ball's going up and it's coming down, but it's also in a car that's moving left or right. So it's going to look different. So to a stationary observer, the clock will go up and down. But to the observer who thinks they're stationary, the clock's going to go up and down. To the observer who is watching the moving target, it's going to look more like this. Okay? Not only will it go up and down, but it's going to go sideways. So let me show you kind of like the math behind this, all right? Now, let me show you this. So let's imagine that we have the triangle here. Okay, actually, I'm going to do this. Okay. So here's my triangle. So this basically is that. Okay. Now, this is simply the stationary observer watching their clock. Okay? And that will simply be a function of two things. One is the speed of light, which is c, times the length of time it takes for that observer. So if I'm the stationary observer, and I can measure the distance this light beam travels, if I just know the speed of light and how long the light beam was traveling for. But if I'm an observer watching someone that's moving, I'm going to see the beam of light do two things. I'm going to see it move left to right, but I'm also going to see it move diagonally. So the left to right motion will be dependent on the medium that's moving and how long it's moving for. Okay? But because I'm observing, so do you remember who sees the slower clock? So the one observing the moving object? Okay. So I'm going to call that the dilated time. I'm going to give it a little apostrophe. Okay. So this is the T represents the time for the stationary individual. That would be Adam in the spaceship. T prime represents the time, the dilated time for the observer watching the moving object. Okay? So then this would be, okay, so if you see if you get this. Remember, the speed of light doesn't change, right? So this is the speed of light times the dilated time, which is the time observed by the person watching the moving object. Now, if we do some trigonometry, we get this. we could figure out the relationship between them, can't we? So what's this formula? What is this? What's that? So we're familiar with that, right? Okay, so let's do some manipulation here. Hey, what's up? So let's expand this, okay? So this will be c squared t prime squared equals v squared t prime squared c squared t squared. So this is just a right angle triangle, right? That's all it is. Okay. Now, what we could do is we can move the t primes to one side. What I'm doing is I'm showing you how this was derived. Okay? Oops, sorry. Okay, so what we're talking about here is this thing called the gamma factor, which is what you see in the equations that determine how much the time is dilated. By the way, dilated means slowing down, okay? Or how much the length contracts, or how much the mass increases. You're going to see this, what is called the gamma factor, which is this thing here. I'm just showing you how this was actually, or this is calculated, okay? So are we okay with what we're doing here so far? Okay, now what we can do is we could divide everything by c squared. So we get this. We get t prime squared minus v squared over c squared t prime squared equals t. Sorry, that should be t2. All right. Now, what can we factor out? We can factor out t prime. Okay. And then we could take the square root. So if we did that, we get t prime times that's what this is. Okay? It's really just simple trigonometry. Here's the thing. You don't have to, I just wanted to show you basically where this formula comes from. You just have to know how to use it. Okay? So this formula predicts, for example, how much you would observe a moving clock to be. Okay? That's the dilated time. In biology, when you dilate something, you make it what? Larger.
Sorry, did someone bring a projector here this morning?
Sorry, hold on. Okay. So, that's because you're going to see that in the equations for mass increase, time dilation. So here's the thing, as speed increases, time slows down, right? But to so like the clocks don't agree anymore, right? Like the person who's on Earth, their clock will be ticking at a different rate relative to the person who's moving. Length will change, mass will change. So we're going to explore this now. Now we talked about the twin paradox, right? We talked about the twin paradox? Okay. So the twin paradox is that if the time is not the same, if the time dilation for person on Earth is greater than the person moving, the person moving's clock is slower than the person that's on Earth. Remember what the solution was for the twin paradox? Because relative to the spaceship, the Earth is moving away. So if you were watching the spaceship's clock, it would look slower. So the astronaut, you would think, would have aged less. But if the spaceship was watching the person on Earth and their clock, it would look like it was ticking slower. So from the astronaut's point of view, the Earthling's clock is ticking slower. So they should be younger when he comes back, or she comes back. What's the resolution to this paradox? Remember what it was? One of the 2 points to undergo like these thought experiments, one of these 2 is violated. Which one? Which one's violated? It's the first one. Because what is the spaceship doing? It's not actually traveling at a constant speed. It has to accelerate, decelerate, accelerate again. So the answer is then the person leaving the Earth is the one who will actually age less. That's the resolution to the twin paradox. Here's some other things that come out of this, which is quite interesting. So I'm going to show you an example of where things that you may think are simultaneous aren't. Okay? So I'm going to show you a scenario. Imagine that you are watching a train. Okay? So here's a train. This is the train cart. Okay? And there's a person inside the train. Okay? So here you are. You're over here and you're watching this train go by. Now, imagine that a bolt of lightning strikes here and strikes here. Okay? Now, the light that you see that strikes the 2 ends of the train eventually will get to you. Okay? Now, imagine those 2 events were simultaneous to you, that they happened at the same time. Right? So you saw the 2 bolts of lightning hit the 2 ends of the train, and for you it looks like it happened at exactly the same time. But what would it look like to the person in the train? So here's the thing. So let's imagine you're sitting in the train. So here I am. Bolt of lightning hits, train's moving this way. Okay? What would you see? You would see something different. That's the thing, right? But remember, the speed of light has to be constant. The speed of light is different than other things like a swimmer in the water. If this was a swimmer traveling this way and you were traveling this way, to you it would look like this swimmer is traveling faster. And if this was a swimmer traveling this way, but you're also traveling this way, this swimmer would look like they're traveling slower. But the speed of light is the same in all reference frames. So what's your conclusion? Your conclusion is the lightning bolts did not strike at the same time. Which one struck first? This one. This one struck first. And then the next one, which would explain why there's a delay in time. Because the actual speed of the light is the same. That's weird, isn't it? Yeah, what you may think as simultaneous, someone's going to say, no, that's not simultaneous. They did not happen at the same time. I'll show you another one which is really freaky, okay? Show you another one that's really, really freaky. Alright, Here's an interesting one. Now, I'm going to show you a video that talks about relativity. So I don't want to talk too much about this, but I want to just kind of like set it up, okay? Set this one up and the next one up too. And because the video's going to talk about it, right? In the atmosphere, when you have like cosmic rays from like the sun striking the atmosphere, they can produce these particles called muons. And we'll talk about particles in the last unit, okay? Now, some particles last a long time, but some last very little. So muons have a half-life of 2 microseconds. So what would that be? What's 2 microseconds? 2 times 10 to the what? Times 10 to the negative 6, right? Seconds. Now, imagine these particles are created and they can travel at the speed of light. And they don't travel at the speed of light. But let's just say, for argument's sake, that they travel at the speed of light. So let's give them the value c, which we know is 3 times 10 to the 8 meters. Okay? How far could these particles travel before half of them decay? How far? Well, it's easy, right? D equals what? C times T, or B times T? C times T. So C is what? 3 times 10 to the 8. T is 2 times 10 to the negative 6. That would be 6 times 10 to the 2 meters, which is 0.6 kilometers. After another 0.6 kilometers, another half would be gone. After another 0.6 kilometers, another half would be gone. In other words, to get to 50 kilometers, that's a lot of half-lives. So if you were on Earth, have you guys done half-lives in chemistry? It's just the amount of time it takes for like half of a substance to decay or be converted to something else. Should you be detecting these particles at the surface of the Earth or below the Earth? What do you think the answer is? No, but should you be? After they travel, and by the way, this is them traveling at the speed of light, and they don't travel at the speed of light. They travel less than the speed of light. But let's, for argument's sake, say that they travel at the speed of light. After 0.6 kilometers, 50% are gone. After another 0.6 kilometers, there's only 25% left, because half of 50. After another 0.6 kilometers, there's only half of 25, 12.5. If you do the calculations, you should come down to a value that is near what? Like half? How many half-lives, in other words, are there to get to 50? Well, each half-life is represented by 0.6 kilometers. What is that, like 8 half-lives? So if you do 1 over 2 to the power of 8, what do you get? What number do you get? What's 1 over 2 to the power of 8? What is that? What is that as a value? What is it? So what is that? 0.0039? So that's like 0.4%. In other words, very few. And again, it's going to be less than that because we are picking a high speed that it doesn't have. But yet, a lot of these particles are detected at the surface of the Earth. So how? How are they going to? Physics says that they should disappear before they get there, but they show up. How's that possible? How is that possible? Okay? Alright, so hold on. Wait. There's another one. So this has to do with time dilation, but that's part of the answer, right? But here's the thing. And the video will talk about that. You can also think of it from the point of view of the muon. Imagine you were the muon. Right? Now remember, time dilation means that if you're observing something that's moving, its clock will be ticking at a slower rate. Well, what if you were the thing that's moving? Your clock would appear what? Normal, right? So from the mu1's point of view, its clock is ticking at a normal rate. So the explanation is different. What we'll talk about in the video is you're going to see two different explanations as to why you can detect them at the surface of the Earth. Okay? We'll watch it and then we'll see if we kind of understood it, right? So, and I'll give you a hint. The second, from the mu1's point of view, has to do with this, with length contraction. Okay? So let me give you another thought experiment. Okay? Let's imagine that you were on a stationary train. Okay? And there's a beam of light that approaches and travels the length of the train. And you measured it, okay? You say, okay, it took X seconds to travel the length of the train. Right? Now, imagine that we are moving towards the beam of light. So the beam of light, and we measured how long it takes the beam of light to travel the length of the train. What would you notice? Now, you're the same observer. I'm not talking about someone watching you from afar, because then the time would be different. You're on the train, okay? And you measure how long it takes the light to travel across the train. Now the train's moving, and you measure it. Well, what should you see? Should it take less or more time? Should take less, right? But here's the problem. The speed of light has to be the same. So what do you think accounts for the difference? Yeah. If you look at the formula for speed, v equals d over t. How do we make this constant? Well, if this decreases, then this has to decrease with it. In other words, the train itself contracts in length. And that would keep the speed of light constant. Let me show you something. And by the way, here's the formula for length contraction. You'll notice the gamma factor again. But we're not going to do any calculations today, okay? We'll talk about that next time. So let me show you the train paradox, which is a neat one, okay? And the video will talk about it. So I'm going to show it, set it up, and then we'll talk about it after we watch the video. So train at rest, tunnel at rest. Does the train fit in the tunnel? They're both at rest. The answer is what? No, because the train's longer than the tunnel, right? Train is what? 60 meters long? Okay. If the train was moving, though, and the tunnel was at rest, special relativity says that the train will be length contracted, which means that it can actually fit in the tunnel. Okay? It can actually fit in the tunnel. However, from the point of view of the train, if you were on the train, it would look like the tunnel is moving towards you. And then the tunnel would look like it's, because the thing that's moving is what's length contracted. So if you were watching from the tunnel and you saw the train coming, the train would look shorter. But if you were on the train watching the tunnel approaching, the tunnel would be shorter. Who's right? We can do an experiment because we can say, in the video talks, now here the thing is about two laser beams that would close the two doors in the tunnel. So imagine that two doors simultaneously closed when the train was in the tunnel. Well, in this frame of reference, it looks like that could work. But what about in this frame of reference? Could it work? No, because the train is what? It's too big. There's no way to close the doors. So what happens in that case? All right, we'll show you the video in a second. The last thing is about mass. Okay? Why does mass increase as speed increases? So, again, you'll notice the gamma factor, but we won't do any calculations today. Okay? There's that gamma factor, which allows you to determine what this mass of an object is when it's traveling faster and faster as approaching the speed of light. Now, we've done collisions, right? Okay? So we've done momentum. So imagine we have a object that has a mass and a speed, and they are approaching each other. Okay? So they're going to collide. Now let me ask you, would that be the same as if we made this stationary? If we made this stationary, how could we conserve the momentum? By making this one travel at what? Double the speed. If you were the red ball and you were watching the blue approach you, it would look like the blue was approaching you at what speed? 120 kilometers per hour. You learned it in grade 11, right? So that makes sense. So if we look at this scenario, if this is approaching at 100, now if these two have the same mass, the law of conservation of momentum says, and if they stick together, that they will move off at half the speed. And if you don't remember that, you can do the calculations. So we've done that in chapter 6 and 8. 5? 5, you're right. 5. Now here's the problem though. What if we were going a lot faster than 60 kilometers per hour? What if we were going 60% the speed of light? Okay, here's the problem. So this ball is approaching this ball at 60% the speed of light. They have the same, supposedly the same mass. In our scenario, the red ball would, in the previous scenario, the red ball would look at the blue one and it would look like it was coming towards it at what? 100. And how did you do that? You just added up the what? Yeah, so here's the problem. If you did that, you would get 120% the speed of light. What's the problem? Can't go faster than the speed of light. So what? That doesn't make any sense then. It's almost like you're violating. It's almost like you're violating the law, because you know the momentum has to be conserved. So what changes then? It's not the speed; it's the mass that changes. So the mass will increase, so the momentum is conserved. Is that weird? It's really weird. This whole thing about special relativity is weird. So why don't we watch the video, and then we'll come back and we'll talk about the solution to the question with the mu1 and the question with the train. So I'm going to pause this right now, okay? Okay, so we watched the video. All right, so what were the two explanations for why we can detect the mu1s at the level of the surface of the Earth? So one is, from the mu1's point of view, the distance is contracted, so they don't have to travel very far to get to the surface of the Earth. But from your point of view, the mu1s, what's changed? What's different? Their time, their biological clock, their clocks are ticking slower. So their half-lives are longer because they're aging slower, right? So that would be the explanation. There's two different explanations for why the muons can get to the surface of the Earth. What about the resolution to this paradox? What's the answer? Who's right? They're both right, because they're not going to agree on the events. One will say that the laser beams, or in the video they talked about guillotines coming down at the same time. So the guillotines will come down at the same time. In the other scenario, that can't happen because if they did come down at the same time, the train would be what? Chopped. So the resolution to that is that the guillotines do not come down at the same time. The front one comes down first, or the laser, in this case, the laser in the front fires first, then the laser in the back fires second. So in this case, they don't agree on simultaneous events. Okay, ladies? So as you saw in the video, the math itself isn't the problem in this unit. It's more of the concepts that we will be exploring. Okay, ladies? That is it. The end.